what we're dealing with right now is called rational function points of discontinuity. And so what we're going to talk about is different things called a zero or vertical asymptote or removable discontinuity. So we're going to use Desmos to also demonstrate what these concepts are. Factoring is going to be very, very, very important. So when you're doing these problems, you have to know how to factor the numerator and the denominator. So what is x squared minus 4x plus 4 factor 2? Now this is what's called the sum of squares. It factors to x minus 2 times x minus 2. And you probably know how to factor if you're in, pre-cal, you know how to factor. All right, so you got negative 2 plus negative 2 is negative 4, and negative 2 times negative 2 is positive 4. All right, and then now we are looking for numbers that add up to a negative 1 but multiply together to a negative 2. So that's going to be a negative 2 and a positive 1, because negative 2 plus 1 is a negative 1. Even though you can't see it, there's a negative 1 right there. All right, and negative 2 times 1 is negative 2. So these are the factors. So what I'm going to do is I'm going to go to Desmos real quick. Let's go to, I'll just type in Desmos. Okay. And what we'll do is we'll just type this in as a function. And you don't have to put y equals. Sometimes you can just put your rational function, and it was x squared plus 4, or not plus, it was minus 4x plus 4. And then in the denominator it was x squared minus an x minus a 2. All right, so you can kind of see you'll see that we factored this correctly. All right, so put x minus 2, x minus 2, and in the denominator I'm going to put x minus 2 and x plus 1. All right, so hopefully you see that these are the exact same graph, that I factored these correctly. Okay, so when we're taking a look at this, I want you to see something that actually happens. So in this graph, this binomial cancels out this binomial, and when that happens, we remove it. So they call that a removable discontinuity. So that's a removable discontinuity, and it's at x equals 2. And if you're wondering why did I say x equals 2, because you plug in a 2, 2 minus 2 is 0. So we have a removable discontinuity at x equals 2. So what would that look like? Let's check. Okay. At x equals 2, I want you to see, can you see right there? It says 2 is undefined, and you can actually see a hole where the arrow is. That's called a hole. It's called a point of discontinuity. All right, so we have a removable discontinuity there. Now, if that wasn't there, then we would say we have a 0, because this actually the number 2 makes this equal to a 0. But since we have a hole there, we cannot count that as a 0. So anything that you can plug in the numerator to make it equal to 0 is called a 0. Anything in the denominator that you can make equal to 0 is called an asymptote. So like, what number could I plug in right there? At x equals negative 1, we have what's called a vertical asymptote. Now, vertical asymptotes are very easy to locate because they're just this line that runs vertically straight up and down. You can clearly see that it's at a negative 1, especially when you're in Desmos. Okay, so we have a vertical asymptote at x equals negative 1. You can see it right there. So when you're working on the Khan Academy, all right, and you're trying to find what's going on, we know we have a vertical asymptote at negative 1, but we have a removable discontinuity at x equals 2. So once again, how do we know there's a removable discontinuity? We know there's a removable discontinuity when these factors cancel out. We have a removable discontinuity. So that's going to be at x equals 2. And we know we're going to have a vertical asymptote at x equals negative 1, because if you plug in a negative 1 in the denominator, it makes everything equal to 0. All right? And last but not least, what are zeros? Zeros are numbers you can plug in the numerator. You're like, well, you could plug in a 2 and make that equal to 0. True, however, if you have a hole at the same place as a 0, the hole's more powerful. It kind of trumps the 0. So in order, these are the most powerful. Okay. Number 1, the asymptote rules over all. So if you have to make a choice between an asymptote and a whole, choose the asymptote. Next most powerful, whole, which is also known as removable discontinuity. I'm not going to spell it all out because it's already spelled out for you. And lastly, a 0. So if you have to choose between an asymptote and a whole, choose the asymptote, because an asymptote's full of holes. And if you have to choose between a whole and a 0, choose the whole. So that's why I'm choosing the removable discontinuity over the 0 for my answer. Okay, so this one will probably be a little bit easier to do because we'll probably have 3 answers here. So let's take a look at this real quick. I'm not going to graph this one. I'm just going to factor it. So a quick little factoring trick, and we'll just do the numerator right now. Let's do the numerator. In the numerator, if I want to factor the numerator, it's very easy. All you're looking for is 2 numbers that multiply together to equal negative 21, but those same 2 numbers add together to equal a negative 4. And so those numbers are going to be negative 7 and 3. Negative 7 and 3. So we're going to put x minus 7 and x plus 3. And now that's all over what? That's all over x plus 13. So nothing cancels out, which means there's not going to be any removable discontinuity. Nothing cancels out. Any number that you can plug in to make this equal to a 0, like a 7 or a negative 3, those are going to be our zeros. So negative 3 and 7 will be our zeros. What number could you plug in here to make the denominator equal to 0? That's negative 13. That's our vertical asymptote at negative 13. So here we did not have any removable discontinuities. Why did we not have any? Because nothing canceled out in the numerator and the denominator. Okay? So we have a vertical asymptote here, and we have 2 zeros here. Okay? I'll go over here, and we'll do a couple more. All right, we're going to do a couple more of these problems and finish up this video dealing with rational function points of discontinuity. So what I've done here, I've taken this q of x function, this rational function, and I put it right in here to Desmos, so you can kind of take a look at it before I start factoring. So there's your function with nothing's factored yet. We're going to go over here and we're going to factor this guy. Okay. So what I'd like you to do is write this function down. We're going to go ahead. I'm just going to make that fraction bar, and we're going to factor the numerator. And then we're also going to factor the denominator. So on this one, what 2 numbers multiply together to equal 21, but they add together to equal 10? All right, what 2 numbers multiply together equal 21, add together equal 10? That's going to be a 7 and a 3, a 7 and a 3. So I'm going to put x plus 7 and x plus 3, just like that. All right, and then in the denominator, it's a little bit different. We're looking for 2 numbers that multiply together to equal this positive 16, the number at the end, but those exact same 2 numbers add together or combine together to equal a negative 10. So what numbers add together to equal negative 10, but they multiply together to equal a positive 16? And that's going to be negative 8 and negative 2. Negative 8, negative 2. So I'm going to put x minus 8 and x minus 2. Now if you want to check to see if you factored everything correctly, what you could do is you could go to Desmos. Go to Desmos real quick. I'm going to make another one. I'll put the divided by. And I'll go ahead and just type them in, right? X plus 7, x plus 3, and then put x minus 8 and x minus 2. All right. So if the graphs totally cover each other up, that means you actually factored it correctly. So that's kind of a good way to practice your factoring if you want to figure that out. Now, here's the thing. the denominators right here, the denominator creates the asymptotes. So any number that makes that equal to 0 is as a vertical asymptote. So we have an asymptote at x equals 8, and we have an asymptote at x equals 2. So I'll put x equals 8. You can kind of see it right there. I'm going to put x equals, all right, 2 right there. Of course, I'm going to change the color a little bit. Let's change that color to, say, orange. Or let's just make the asymptotes green. Look, yeah, that's probably good. All right, so there's our asymptotes right there. Now, where are our zeros? Our zeros are at -7 and -3. If you click right here, you can see there's a -3, there's a -7. So we have 2 zeros right there for our rational function. So when I'm doing the work, when I'm writing stuff down, I want you to understand is here we have no removable discontinuity. There's no answers because nothing cancels out in the numerator and the denominator. All right, so where were our zeros located? At -7 and -3. So we have a 0 right here, we have a 0 right here. And where was our vertical asymptote located? Right here at an 8 and right here at a 2. So at 2 and an 8 we had vertical asymptotes. And that's why I'm going to select those answers. All right, so, we go over here. We have a 0 at -7, -3. We have asymptotes at 2 and 8. All right, let's do one more and see what happens here. Hopefully this will help you in solving your problems. Not your problems in life, but just your math homework problems. All right, so what is this factor to? What are two numbers that add up to 8, but they multiply together to equal 16? Well, that's going to be x plus 4 and x plus 4. Because 4 plus 4 is 8, and 4 times 4 is 16. What two numbers add up to 6, but multiply together to equal 8? That's going to be 4 and 2. So x plus 4 and x plus 2. I think we've done this one. I don't know. But anyways, these cancel out. So what happens when things cancel out? That's called removable discontinuity at what number? -4. So we have a removable discontinuity at -4. However, it says we have a 0 there too, but what's more powerful, a 0 or a whole, or a removable discontinuity? This is more powerful. And then we have a vertical asymptote right here at a -2. So we have a vertical asymptote at -2 and removable discontinuity at -4. Okay, let's do one more. This one won't take long. Okay, we're going to factor the numerator. One thing you can pretty much count on right here, we know we don't have to worry about factoring it. You're done there, okay? So we're looking for two numbers that multiply together to equal +20, but those same two numbers add together to equal -12. What are my factors of? Ooh, I got it. -10 and -2, -10 and -2. Because -10 plus -2 is -12, and -10 times -2 is +20. Yay, we found the factors. Oh, these cancel out. So even though you thought you had a vertical asymptote at 10, all right? Now you cancel out, so you would think is it a whole or is it an asymptote? That's interesting. So how about this? Let's go ahead and look at Desmos and see what we can figure out. All right, we definitely have a 0 at a 2. Totally have a 0 at a 2. So let's go to Desmos and figure it out. All right, so I'm going to take this, go to Desmos real quick. Clear that out, clear that out, clear that out. All right, do a little deleting here. I'll put x minus 10. And then up here, we had, I'll put the factors here, x minus 10. And then we had parentheses x minus 2 right there. All right, but these cancel each other out. So it looks like we just have a whole at 10. Let's look. Hey, look, we have a whole at 10. Do you see any asymptotes anywhere? I don't see any asymptotes. Do you? I do not. All right, so I don't see any asymptotes. All right, so we have a removable discontinuity at 10, and then we have a 0 at a 2. So what happens when these cancel out? It's not an asymptote. It's going to be what's called a removable discontinuity, or a hole. So we have a 0 and a hole. All right, I hope that was helpful. Good luck doing the assignment.